Good day, ladies and gentlemen. We are doing our last topic, corrosion and degradation of materials. So in the introduction, we'll cover what's corrosion. What's corrosion? Corrosion is the corroding of materials due to its interaction with the environment. And typically this now affects our mechanical properties, your tensile strength, ductility, and even hardness. And this happens as a result of electron exchange for metals. While for ceramics, which are a bit inert, this happens as a result of change in temperatures. And why study corrosion? The corrosion has economic implications. So the need to replace these materials after a certain time obviously have an effect on economics. And also there are consequences. If these materials are not replaced, or if the corrosion occurs without our acknowledgement or our knowledge, there will be consequences like collapsing of buildings or reactors. We look at metal corrosion, and you have already said the process that takes place is electrochemical process. That's the exchange of electrons. And so basically during corrosion, two things take place. There's oxidation on the anode, and basically oxidation is the losing of the electrons. Then there's reduction on the cathode, which is basically the gaining of electrons by ions. And as shown in the figure on our left, basically our zinc solid will dissolve into the acidic solution and it will produce electrons. These electrons are taken or absorbed by the hydrogen ions to produce the hydrogen gas. And the overall equation is given there at the bottom. So what determines the extent or the ease at which this happens is based on electrode potentials, and this is based on thermodynamics. So if you remember well your thermodynamics, for a reaction where delta G is negative, this tells you that the reaction is feasible. It doesn't tell you how fast it is, but it just tells you that it will happen. It might be fast, might be slow, but the reaction will happen. So in this case, delta G is equal to minus N Fe, where F is a Faraday constant, N is the number of electrons involved in the reaction. So you'll notice in this case that if delta G is negative, then our E is positive. So for these electrode potential, for these kind of reactions, our positive electrode tells us that the reaction is feasible, because that will translate to a negative delta G. A negative one will translate to a positive delta G, and this will tell us that the reaction is not feasible. And a typical setup is given on the diagram on the right. So we have two electrodes in their solutions, and the solution concentration should be around 1 molarity, and there's a membrane separating these two, but the membrane allows the diffusions of the ions. And then we have a circuit that allows the transportation of the electrons, and for this case the voltmeter will read 0.32 volts as shown in the other equation. And so this voltage is the one that kind of represents the driving force, or the extent to which this, or the ease at which this is expected to happen. So I'm sure we have come across the standard electromotive force series. So we have a list of metals, and there is no intrinsic value for the EMF for a particular metal or system. So what is used is a reference cell, of hydrogen, the one in our left hand side, we have a cell of hydrogen where hydrogen is being pumped to the cell, and the concentration of the ions is 1 molarity, and platinum is used, and this is collected to the other electrode, and the reading there is what to tell us what the EMF for the other material that you have connected with. And the use of the platinum is just to provide a surface area where oxidation and reduction of the hydrogen or the hydrogen atom ions can take place. And this is a typical standard electromotive force series. So we have the positive values and the negative values. We have already said if it's positive, it tells us that it's feasible for that reaction to occur, while if it's negative, we will expect the reaction to go the other way, not the way it's giving us a negative value. So the earlier work was done at standard conditions. This is at 25 degrees Celsius, 1 molarity ions. If there's gas, this is at 1 atmosphere. But obviously corrosion or these reactions will take place not at these standard conditions. So in this case, we're looking at the effect of concentration. So what is used is the Nesta equation. So saying the electrode potential for the system is equal to the standard electrode potential minus R times T divided to Faraday constant times lean brackets concentration of zinc over concentration of zinc ions. And in this case, R times T over F at 25 degrees, that value becomes that. And we'll look at a simple example here. We have copper in this setup being the cathode, meaning oxidation is taking place, and you have zinc at the anode, meaning reduction is taking place. So for us to find the standard electrode potential for the system or the cell potential for the system, we will subtract the zinc minus the electrode potential for the copper, and that's where we'll get minus 1.1. Then the other things we'll just plug in the equation. Then if we had the concentrations of our products of our reactants, then we'll put them, then you'll get what is the electrode motive force for this system under these conditions. So basically here what you're looking is the ways in which the corrosion can be analyzed. So the next system that you're going to look at is called the pipe box diagrams. So this is also built on thermodynamics. It relates potential and pH, and we'll look at the example given here for water, or maybe before that, what is its aim. So its aim is to tell us how species will behave at varying potentials and varying pH. So our y-axis is potentials, whilst our x-axis is a pH. Here an example for water is given. So that typically the equation that will be used to get this graph. So in this graph we have 3 regions. The middle region where water will be thermodynamically stable. Then we have 2 regions where we expect the water to evolve oxygen, and then we have and become acidic. Then we have at the bottom place we expect to evolve hydrogen and become alkaline, and this will see it being incorporated in a number of systems where water is included. We'll just look at one system. So this is a system for ion. So in this system, there are a number of regions, obviously. So a region where there won't be much corrosion, it will be a case where you've already formed the oxide, and this oxide will protect the metal. So we will want our system to be at these conditions where we get these oxides. And maybe other important things to note here is that horizontal line represents a direction that does not involve pH or ions. So typically we have a region separate where we have a straight line above ion. You will notice a line that is horizontal. So in this case, we are saying we have this possible reaction where we have two ion 2 plus 2 electrons to produce ion, and this is what this equilibrium line represents, this horizontal line, that you have those two reactions being at equilibrium on that line. And then above we have more of the ion 2 plus, at the bottom we have ion, then that's the equilibrium line. And we are saying it doesn't evolve hydrogen or the hydroxide ions as seen by the equation. Then we have a case where we have a vertical line, and this is around 1.75. So in this case, around 1.75 pH, there is no change in the potential. So this tells us that in this case, this reaction does not involve ions or electrons. It does not involve electrons, but it involves the hydrogen plus and the hydroxyl ions, and that's the region. I think those are the major things that we need to take from this picture. Then we also have those three regions for water, where at the top we said the water is not stable, in between is stable, at the bottom it is not stable, it involves hydrogen. And I think, as we spoke earlier, we emphasized that the earlier cases that we're looking at are based on thermodynamics, and these give us no information about the rate at which corrosion takes place. But for design purposes, it is important to know how quick or how fast corrosion will take place and how fast the material will lose its important mechanical properties. So what's usually used is called concentration penetration rate, and that's the equation given there. And in this case, T is time, rho is density of the specimen, and A is the area of the specimen, and K is a constant based on the units or that the other properties have been used. And we'll do an example for this. And typically an accepted CPR should be less than 0.5 millimeters per year or 20 millimeters per year. So this brings us to just general concepts about corrosion. Then what we'll look at next after we've done a tutorial is we'll look at specific corrosion types, how they occur, how they can be prevented, their mechanism, and such stuff. Thank you. Our reference textbooks are these two books, and you can also make use of another paper, any other materials. Make sure you attempt the examples given in these two books and understand them.